Hello and welcome to lecture number 8 in the course Advanced Robotics Applications. In the last class, we discussed about the inverse kinematics of the Puma robot, and then we moved on to looking at sensors, the different kind of sensors that are there. So today we'll complete our discussion on sensors, and then we'll move on to actuators, after which we will move on slowly to linear control systems. Okay, so in the last class, we talked about touch sensors, the different kind of sensors which are there. We are very briefly going through the different sensors and the need for sensors. We have seen that apart from the internal sensors, which are potentiometers, which are position sensors, then there are velocity sensors and acceleration sensors. We also need other kind of sensors, which can be contact sensors, and then we also need sensors which can detect obstacles in front, which can be non-contact type. Okay, so the next type of sensor we saw was the on-off switches, which are contact sensors. And as I was mentioning in the last class, that these contact sensors are required to understand or for the robot to figure out where is the 000 of the system. So wherever we have 000 of the system, the robot would move first in the homing position, contact the base 000 sensor, and that's where it can figure out that where is the 000 or the home position of the robot or an NC machine or any other system. And that happens because with the position, with the actuator, which is normally a motor, there is an encoder, and an encoder is an incremental device. So you do not know where is the absolute position. So to find out the absolute position, we need some kind of contact sensors, and these contact sensors tell the robot the range of motion of each of the joints, as well as what is the zero position of the robot in terms of the contact sensors. Okay, the other kind of sensors which are there now, these contact sensors are basically of the on-off type. So on-off kind of sensors are like the keys in your computer keyboard, which operate basically on the on-off kind of principle. So essentially, if it's a switch, so when it is pressed, a contact is made and it is taken as on. So the moment the contact is broken, it is taken as off. So we have on-off kind of switches, which are basically basically similar to keys of laptops and computers. Okay. Now, the other kind of sensors which are used are the non-contact type. For example, this is a non-contact out of the non-contact type. For example, if there's a mobile robot which is moving, say for example, this is my mobile robot, these are the two wheels and there's a caster wheel, and there's an obstacle in front. Now the robot doesn't need to touch the obstacle. Okay, so from some distance it should be able to figure out that there's an obstacle, and either it should change its path and go left or go right. Okay, so these are basically what are called non-contact sensors, and they're of different types. Okay, so let's move on to the next series of sensors, which are basically external sensors. So these sensors are falling under the category of external sensors. Okay, now there are different kind of sensors which can figure out proximity. Proximity essentially means how close an object is to the robot. For example, there are many applications. For example, one can be a mobile robot which is moving around, there's an obstacle in front. The other can be a very simple application like a conveyor. So there is a part which is coming in a conveyor. So there is a conveyor which is moving and a part is coming. Okay, and this is a robot which has to go and pick up the part. Okay, so the robot has to pick up this part. So essentially what it means is that the robot has to go here, catch the part and pick it and maybe place it somewhere, or maybe drop it in this and drop it in a bin. Okay, maybe it has to come this side and drop it here. So when the part has come, there has to be a sensor which will tell the robot that the part has come. Okay, so there will be some kind of sensor here which will tell the robot that the part has come. Now this sensor is also of non-contact type. So the sensor is not supposed to touch the object. Okay, because it can damage the object or the sensor. So normally such sensors are non-contact type. And one example is the proximity sensor, or an inductive sensor, which is used to check the arrival of a part on a conveyor. So when the sensor senses the part has come on the conveyor will stop and it will inform the robot that the part has come. The robot will then go and pick up the object, put it somewhere, and then again inform the conveyor that the part has been picked up. Okay. So basically what we see is that there are many applications where sensors are required, where there is no contact between the object and the robot, and such sensors are called proximity sensors. So the first type of proximity sensor is an inductive sensor. How it works is very simple. Okay, there is a copper coil as shown in this figure. There is a coil. So this part is the coil, and at the back side there is a magnet. Okay, so as shown in the figure below. Okay, so this is a magnet, north-south magnet is shown there, and there is a cylinder, plastic cylinder maybe, and there is a coil, copper coil, which is wound on the cylinder. Okay. Now if you look at this bottom figure, what we see is the lines of force are moving like this, which means that the lines of force are not going into the coil, or they are not cutting the coil. Okay. But the moment an object comes in front, as shown on the right hand side, suppose a ferromagnetic material or iron, a material made of iron comes near it, what would happen is the lines of force will be pulled out. So the lines of force was like this, so they'll immediately be pulled out. So let me change the color. So the lines of force will be pulled out like that, as you can see, because the ferromagnetic material has come in front. So because of magnetic induction, the lines of force are going to be pulled out like this, and they are going to cut the lines of force. They're going to cut the coils. Okay, so when the lines of force are being pulled out from here to here, they're cutting the coil. You can see that. Now the moment the magnetic lines of force cut the coil, what will happen is it is going to induce an EMF. So it is going to induce an EMF. Okay, so when the EMF is being induced, it basically means that a voltage is being generated in that coil now. So when the lines of force are not passing through, the voltage is 0. When the lines of force are passing through, the voltage is V. So basically it's like an on-off. So the moment the object comes in front of the sensor, as shown on top here, okay, what will happen is on the magnetic lines of force of the sensor will start passing through the part here, and it is going to induce an EMF in the sensor, which basically the sensor understands that a voltage has been generated, which means a part has come. So immediately the conveyor will stop, and the robot will go and pick up the part. Okay, then the robot will again inform the conveyor that the part has been picked up. So this type of a sensor is called a proximity sensor, proximity inductive sensor. It is called inductive because it is using the principle of induction. Okay, so an EMF is being induced in the copper coils. Okay, so this is a sensor which is very commonly used in industries to figure out iron and steel parts. This is another sensor which is also a proximity sensor, but it works on the Hall effect. So this is called a Hall effect sensor. Now how this works is pretty similar to the one that is used to the previous sensor, which is an inductive sensor. Now on the left hand side, we see that this is showing a Hall effect sensor. So there is a horseshoe magnet and there are lines of force. So in the horseshoe magnet, the lines of force will be traveling like this, and the Hall effect sensor is placed in there. So what is the Hall effect sensor sensing? It is sensing either the absence or the presence of lines of force. Okay, so in this particular case, what is happening? The lines of force are passing through the Hall effect sensor. Now if you look at the right hand side, what is happening? The lines of force are being pulled out because a part has come in here. Again, it's a ferromagnetic body, maybe iron or steel. So what is happening? The magnetic lines of force are being induced in this ferromagnetic body. So the magnetic lines of force are being pulled out like that. So in this case, the lines of force are not moving into the Hall effect sensor. So essentially, it's a 0 and that's a 1. Or this is whatever, this is a 0 and that's a 1. Okay, so basically what is the sensor sensing? Whether the lines of force are passing through it or not. So the moment the ferromagnetic body comes in front, the magnetic lines of force are not passing through the sensor anymore, and hence it can detect that something has come in front. It's a proximity sensor because there is no contact. Okay. Now the other kind of sensor, just to mention that this Hall effect sensor is very effectively used in cars to measure the speed. Okay, so the speed of the car is measured using Hall effect sensors in the gearbox. So the output of the engine, so you have an engine, suppose in the engine we have a crankshaft. Okay, so this is the output shaft of the engine. So in the engine there is a projection of the shaft. On the shaft there is a projection like this. If I take the side view, this is the projection, and there is a Hall effect sensor which is there. Okay, so the moment, so maybe the Hall effect sensor is here. This is as shown in this figure here actually. Okay. So once the crankshaft is rotating, for every one rotation, the Hall effect sensor will detect this projection once. Okay. Now in the case of the speed of a car, the gear output in the gearbox also contains a Hall effect sensor. So in the gear output, again there will be a small projection on the output shaft of the gearbox, and when it is rotating, it is going to the Hall effect sensor is going to simply detect how many times it has rotated. Okay. So this is extensively used in measuring the speed of a car. So the other kind of sensor is an ultrasonic sensor. Ultrasonic sensor works on the principle of ultrasonic waves. Now, what the sensor looks like is something like this. On the left hand side, which you can see is the sensor. Now, this is a ceramic transducer, like a piezo. What is a piezo? The piezoelectric crystal. So, piezoelectric crystal. Okay, so piezoelectric crystal is used here as the ceramic transducer. Now, in a piezo crystal, as you know, that if you apply pressure, it will generate charge. Okay, so plus, 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 minus, minus, minus. Okay, and if you give it a charge, it will generate pressure on the other side, like that, right? So essentially, in a piezo, if you give it electrical charge, it will generate pressure, and if you give it pressure, it will generate charge. So it works vice versa. So how this works is, this ceramic transducer, which is here, is charged at a particular frequency, which is shown here. So it is charged, so charge is given to it at this frequency. Okay, this is charge being given. Now, the moment charge is given, what will happen is it will expand. Okay, as shown here. If you give it a charge, it will expand. Once it expands, there is a very small pressure that comes on this resin here. Okay, so it is being charged at a particular frequency. So this is going to expand and contract at that particular frequency. So it will expand at given frequency. Okay, at the charging frequency. So when this is expanding, what is happening is this resin is vibrating and there is air here. So what will happen is this sound waves will be created, and the sound waves will travel like this. Ultrasonic waves or sound waves will be transmitting outward like this. The sound wave will hit an object and come back. Okay, and the moment it comes back, it is going to hit the resin again. So the moment you apply a pressure, a charge will be generated. Okay, so it is vice versa. Okay, so this is what is showing. The second graph here is showing this is the charging frequency. It is being charged at that frequency. Okay, and the wave is going out. It's an ultrasonic wave which is going out because of the vibration of this resin here. And then what will happen is the wave will come back, hit something, come back, and the moment it comes back and hits the transducer again, it will generate a charge which is here. So if you know this distance from here to here in the time interval, if you know that del t, you know the velocity of sound in air, and you know the time interval. So you know how much time it took to go, or you can calculate the distance where this fellow has gone till here, hit and come back. Okay. Now this is used for obstacle avoidance. Okay, so in mobile robots for obstacle avoidance, in cars for rear parking, this ultrasonic transducer is used. This ultrasonic sensor is used, and the ultrasonic sensor basically uses this piezo crystal as the transducer. Okay, now this is a very cheap sensor. It's very easy to control. We have experiments on this. So as we move on to the experimental part, we are going to see how the experiments are being how the mobile robot can avoid obstacles. Okay, in the rear parking of cars, in the back side of the cars, if I draw the rear side of the car here. Okay, so if this is the rear side of a car, on the rear you would see this rear parking. There are sensors like that for rear parking. Okay, which tells the distance of an obstacle from the car. Now these are ultrasonic sensors. Okay, so ultrasonic sensors have wide application. They are very simple in use, but very often they do not see. Now why don't they see, or they don't detect? So very often, if the surface from which the wave is hitting has an angle like this, so what will happen? The wave will hit that angle and go away. Okay, suppose the object has an angle now like this. So the wave will hit this and then go away somewhere else, which means that it will not come back to the sensor. Okay, so the sensor will not see the obstacle. Okay, so ultrasonic sensors are very good, but they are also very bad in a way that sometimes they don't see. The other is if the ultrasonic sensor, if the ultrasonic signal, so if the sound wave is absorbed, okay, in the material itself. So for example, if this material here absorbs ultrasonic waves or sound waves, then obviously the wave will not come back. So the obstacle will not be seen. Okay. So what we do in a mobile robot is, if this is a mobile robot, the top view, and these are the wheels, we put ultrasonic sensors normally all around the robot like that. Okay, or we have an ultrasonic sensor which will scan, so it will move. So first it will move to this side. Okay, So it will move this side and it'll move the other side. First you'll see this side, this side, this side, this side, this side. So we mount the sensor on maybe a servo motor, and the motor will rotate so that it can see all sides. And then if there is an obstacle in front, okay, or wherever the obstacle is, it can figure it out. Okay. So these are three sensors, which are proximity sensors: the inductive sensor, which works by magnetic induction; the Hall effect sensor, which also detects the magnetic lines of force. Okay, and this one is very commonly used. The other is the ultrasonic sensor, which works on the principle of ultrasonic waves. So a wave goes out, hits, and comes back, and it generates an ultrasonic this ultrasonic wave. The time of sending the wave and the time of receiving the wave, if we know the time distance between them and we know the velocity of sound in air, then we can very easily find out what is the distance of the object. Okay. Now, touch sensors, as the name indicates, these are basically for touching. So how it works is, so it is shown here, the touch and the pressure sensors. So there are conducting layers. So the conducting layer one is like this, and the other one is like this, and there is in between there is another non-conducting rubber. So if you press here, what will happen is this rubber will go through that hole and touch this other part, and that means it'll start conducting. Okay. So this is a pressure sensor. It can also be used as a touch sensor or a contact sensor. This is another sensor, which is a pressure sensor, in which case there is this electrodes. So these are electrodes, and there is some distance between the electrodes. So when you press, what would happen is this conducting rubber will get inside those, or get in between those electrodes. So if it gets in between those electrodes, what will happen? It will start conducting. That means current will start flowing through them. Now, depending on the amount of pressure that has been applied and how much of this conducting rubber that has gone in between these two electrodes, that much of current is going to pass through. So the more pressure you apply, much more of this material will get in between those two sensors, between those two electrodes, and more current is going to flow. So we have some kind of calibration between the pressure and the current that is flowing in the conductors, okay, which can be a straight line. So this is a pressure sensor, this is a touch sensor, the previous one is also a touch sensor. Okay, so these are electric connections here, and this is something like a printed circuit board. So when you press, what will happen is if you're pressing in this area, that place will short, and you know exactly contact has been made there. Let us move on next to actuators. We have talked about sensors. We started off by talking about encoders, then potentiometers. Then we talked about the DC motor, which can be used as a sensor. Then we talked of non-contact sensors like the inductive sensor, the Hall effect sensor, ultrasonic sensor, most commonly used. We have all these sensors during the experiments, so we'll be looking at the experiments with these sensors in detail, how to read the readings of these sensors using a microcontroller, and how to use these sensors for robotics applications. Now, the next what we need to look at is, we saw in our closed loop control system, we have sensors, which we studied just now, and in most applications, the encoder is used. Okay, the incremental encoder, that is the one used in 95% applications in robotics. The next is actuators. So in actuators, there are different kind of actuators. We can have electrical actuators, we can have pneumatic actuators, hydraulic actuators, advanced actuators. Okay. Now, electric actuators basically are divided into stepper motors, DC servo motors, AC motors. Okay. Now, electrical actuators, as the name indicates, the energy input is electrical current and the output is mechanical motion. Okay. Then we can have pneumatic actuators. Now, pneumatic actuators are those in which operate using air pressure. So something like a piston cylinder mechanism. We'll give it air pressure, and based on that air pressure, the piston cylinder will move in a particular direction, and that causes mechanical motion. You can have hydraulic actuators. In hydraulic actuators, the fluid being used is oil. So these are also piston cylinder mechanisms. So they'll be something like this. Let me draw the piston cylinder mechanism. So there's an input and there is an output. So this is something like a piston cylinder mechanism. So this is my inlet and this is my outlet. So if I put air into this, then it's a pneumatic actuator. If I put oil into this is a hydraulic actuator. Okay. Then there are advanced actuators like ultrasonic motors, artificial muscles, molecular motors. Okay. Now these are very useful for in the micro domain. So micro, nano domain, these are useful. Okay. Now so we talked about the electrical actuators, stepper motors, DC servos. Now the interesting question, or the important question, is where would you use which actuators? Okay. Now in the case of a robot, very often, okay, the base joint of the robot carries the maximum weight. So the base joint, suppose it is rotating about this axis, is called the waist or the base joint. Okay. Now this carries the maximum weight. Now very often the base joint carries the maximum weight, so basically we use a hydraulic actuator there. So which actuator is the most powerful here? So this hydraulic fellow. So the hydraulic actuator is the most powerful actuator out of all this. Okay. Pneumatic is the weakest, and in between is electrical. So when we are using in case of grippers, when very high pressure or force is not required, then we normally use a pneumatic pressure, or the grippers are very often pneumatic. Okay, they work with air pressure. Now the other advantage of using air pressure is that they are back drivable. What this means is that suppose there is a piston cylinder mechanism using air, and suppose there is a force here. What will happen is the piston cylinder will just go backwards. So it means that suppose a robot is holding an object and it hits something, then the gripper has to open and release the object, right? That is basically ensured by using a pneumatic gripper. So it is the weakest and the safest. Okay, so this is also the safest actuator. Okay, because it is back drivable, because air pressure cannot apply very high pressures. Okay, so if you require very high weights, now what kind of weight? Suppose the robot has to pick up 100 kgs. Okay, then you may go in for hydraulic. Okay, and very often the base of the robot is hydraulic in industrial applications. The gripper is pneumatic. Very often it is having this structure, hydraulic. So hydraulic, then pneumatic is the end effector, and in between it is electrical. Electrical is the most common used because it is the easiest to control. Okay, and electricity is available everywhere. Now, in case of pneumatic and hydraulic, you need to keep a air cylinder or a tank to store pressurized fluid. Okay, so you need an additional tank to give you pressurized oil or pressurized air, which is not required in the case of an electrical actuator. Okay, so first let's look at electrical actuators, which starting off with stepper motors. Now, stepper motors, as the name indicates, they move in steps. Now, how do these stepper motors work? Okay, now we have studied about the DC motor, which I explained in the last class, where you have a rotor and you have a stator. Okay, and the windings are on the rotor. Okay, the stator is a permanent magnet. Now, in this case, in the stepper motor, what we see is that this is the stator. Now, the stator has teeth like this. Okay, and the rotor, this is the rotor, and the rotor also has teeth. Now, the rotor also has teeth. Okay, now how this operates is the stator has these windings or coils on these teeth. So if you activate any of the coils, suppose I give a voltage to the coil, what will happen? A magnetic field will be generated. Now this magnetic field will induce a magnetic field onto this rotor. Okay, so if it's a north-south, it will become a north-south here. Okay, so this induces a magnetic field onto this rotor, which is normally a ferromagnet. So this is a ferromagnetic rotor. Ferromagnetic rotor or a magnetic rotor. So what would happen is an opposite pole is induced into the rotor, because of which the rotor will be attracted. So this will get attracted to that pole now. Okay. Then what we'll do is we will activate the next pole. I will give a voltage to this one. Then I'll cut this voltage and give it to this. So what will happen is it will generate a magnetic field. This magnetic field is going to induce a magnet onto this one now. So this will move in that direction and get aligned. Okay. Then I will activate this one, then I'll activate that one in that sequence. And each time I activate, what will happen is the motor is going to move by one step. Okay, and hence it is called a stepper motor. So now you understand why it is also called a stepper motor, because it moves in steps. So as shown in this figure here, we are activating pole B, as shown here, sequence of rotation. We are activating pole B. 6 is getting attracted there. Then we're activating pole C, as shown here. The teeth or the pole C is being activated. This one, number 5, gets attracted there. So what you have seen is that this has moved by one step. Then we activate D. This is D. So what happens? This gets aligned. Then we activate A dashed, which is this one. This gets aligned. Okay, so B, C, D, A dashed is the activation sequence for clockwise rotation. So it is rotating clockwise. Now suppose you want to go anti-clockwise. All you have to do is to just reverse the sequence. Then A dash, D, C, B will give you counterclockwise rotation. Now this stepper motors can also be operated in what we called micro-stepping. Now what is micro-stepping? It essentially means that I'm going to apply, what we were doing is we were applying one voltage to one of these coils. We are applying a voltage here. Now suppose I activate both the coils, V1 here, V2 there. So what will happen, it will be attracted by this one and it will also be attracted by this one. Okay, now where will it go? So if the ratio V1 by V2 is greater than 1, then it will go towards V1. If V2 is greater, it will come towards V2. And if they're equal, what will happen? If they're equal, then the pole will come exactly in the middle because it has equal attraction from both sides. Okay, so we can control the position of the rotor even for in-between positions by varying this ratio V1 by V2 is equal to A. So by changing this ratio, we can actually vary the position of the teeth where it will go and stop here, here or here. Okay. So this is called micro-stepping, and you can do in a single stepper motor. We normally go 1.8 degrees per step. In micro-stepping, you can go very fine, 0.02 degrees also is possible. Okay, you can go very fine steps. Okay. Now you can have megatorque motors. These are also stepper motors, but in the previous case, what we saw is there is one rotor. So there is one rotor here and one stator. But in the megatorque motors, there is more than one stator. Okay, so there is a stator on this side and there is a stator on that side, and this is the rotor now. So this is the two-tailed rotor. This one is the rotor. Okay, so because the magnetic field is being applied from two directions, this is much more powerful than the previous one. Okay, we can also have linear stepper motors. So this is a linear stepper motor as shown here. Now working is very similar or almost same as that of the rotating stepper motor. Suppose these are the poles, so we can call this the stator, and the bottom one can be called the rotor. Okay, so what is happening is if I activate this one, what will happen, induce a magnetic field onto this teeth and it will be pulled here. Okay, then I activate number 4, so this teeth will be pulled there. Then I activate number 2, so what will happen, this teeth will be pulled there, and then I activate number 3, this teeth will be pulled there. So what has happened is that this fellow has moved in this direction. Okay, and it's the linear stepper motor, so this is moving in this direction slowly, one step at a time. Principle of operation is exactly the same. So if I reverse the sequence, what will happen is it will again go in the other direction. DC motors we have explained in the earlier case, where the basic principle of working of a DC motor we have seen. Now in a DC motor, we give it a voltage. So this is my input voltage. Okay, this is my plus minus input voltage. This is the commutator ring. And when I give it a voltage, what happens? There's a current which is going in the conductor. This produces a magnetic field which interacts with the magnetic field of the rotor. Okay, and hence there is a rotation. Okay, but there are some disadvantages of this motor. What are the disadvantages? One is there is a commutator, and in the commutator, why is the commutator required? Because to change the polarity. Okay, so this is required to change polarity. So when this coil is rotating, what is happening is that after every rotation, there is a change in the polarity of the voltage induced in there. Okay, so what we can do is to use the commutator basically to change the polarity so that the polarity or the direction of voltage in the coil and the direction of the supply voltage is the same. Okay, now that causes a problem. What kind of a problem? The kind of problem that we see here is that to maintain contact with the commutators or a split ring, this is called a split ring also because the ring is split in there, okay, we have to use a carbon brush to make the contact. So the voltage is, or the connection is given through the carbon brush. Now, because there is a brush here, there is friction at this point, okay, there is friction. And once you give, once there is friction in there, because one is rubbing against the other, because of friction, it is going to wear off. Wear and tear will be there. Okay, so once there is wear and tear, after some time the carbon brush is gone. You have to replace the brush. The other is because of this brush, there can be spark, okay, and there is chance of noise in the system, plus there is friction. So if you're looking at the voltage versus the speed of this motor, if I'm looking at voltage versus speed of this motor, then it should theoretically be a straight line. But because of this friction, what will happen is it will become a little bit like this, then become straight, then become like that. Okay, so in the starting and the ending portion, because of friction, it will not be a straight line, it will become non-linear there. Okay, so for an industrial application, this is not used essentially because once the brushes wear off, you have to change the brushes. So in the case of a robot, say for example, if you have to change the brushes, you have to open everything and then change the brush. There is chance of spark, okay, and plus it is non-linear like this. So in terms of control, there is a problem. So for industrial applications of robots and CNC machines, what is done is we do not use brush motors, but we use brushless DC motors. What is the basic difference? Let's go back here again. In the brush motor, we see that the coil is the rotor. That's the rotor. Okay, and the permanent magnet is outside. Whereas in the case of brushless motor, so this is a brush motor, this is a brush type motor, in which case the coils are inside, the permanent magnet is outside. But in the case of a brushless DC motor, what we see is that the coils are outside on the stator, and the permanent magnet, this is not a permanent magnet, these are strip magnets, or the magnet is inside on the rotor. Now this also, when the rotor is rotating, we have to change the polarity. So for that we have to use electronic commutation, okay, what is called electronic commutation. Commutation, T-A-T-I-O-N. Okay, which means changing the polarity. So electronic commutation is used for changing the polarity. Okay, and so as the rotor is rotating, as in the previous case, what we saw is when the rotor is rotating, what will happen is you need to change the direction of the supply voltage. Why? Otherwise the direction of voltage in the coil and the voltage that is being supplied will become different. Okay, so in order to avoid this, what is done, the polarity in the coil is changed, or the polarity in the coil automatically changes in this coil. Okay, so the rotating coil, the polarity automatically changes because of the slip ring which is provided there. Now in the case of the brushless motor, there is no slip ring, but it needs to know, it also needs to change the polarity. Okay, so how does it know what is the position of the rotor? So it basically knows the position of the rotor by using this 3 sensors. These are also Hall effect sensors. So this can be Hall effect sensors which are used to detect the polarity of this rotor. And based on the polarity, the electronic commutation automatically changes the supply voltage being given to the motor. Now for that, these motors are more expensive because you need to provide for electronic commutation. There is this Hall effect sensors which are there. Okay, and these magnets which are there are very, very expensive. Now the issues of brushless DC motor is that the motors are used in all robots, then NC, CNC machines, aircrafts. Whenever you use industrial applications, brushless DC motor is used. Okay, not brush motors. But brushless motors are more expensive. So the disadvantage of this is that they are expensive. Okay, and there are very few companies which make the magnets. So the most heart of the motor is the magnet. So if these magnets are not made proper, then what will happen is, what do I mean by proper? So if the magnet is very heavy, what will happen is that you cannot break the motor. That means when you're trying to stop the motor, and when the motor is rotating, you're doing position control. So you're trying to stop the motor after reaching the desired position. If it is very heavy, it has very high inertia, it will not stop. Okay, so the rotor has to be light. So the rotor has to be light in weight, okay, for better control. But the magnets must be very strong. Okay, and that is one of the problems of well, it's not a problem. It is the reason why this brushless motors are very, very expensive. Okay. Now, you would have also heard the word servo motor very commonly. So a DC motor, which is in closed loop control, is called a DC servo. So a DC motor working in closed loop position control is called a servo motor. Okay. So this is my motor. This is my DC motor. This is the optical encoder of the position feedback. This is the controller, and this is in closed loop control. Such motors are called DC servos. And nowadays we can buy very, very cheap motors, okay, which come in a box, okay, and there is an output of the box which you can directly connect to the link of the robot, and you can use it like this. Okay, that means the controller, the actuator, the motor, the encoder, the feedback device is all enclosed inside the box in one package, and this comes in a small package. And the package has an output link. You can just connect your robot link there, and you can use it like a robot link. Okay, so this is what is a servo motor. So this servo motor is essentially a DC motor. So there is a DC motor here, which is connected to a gearbox. There is a potentiometer, which is the position sensor, and this is the PID controller. So this is a PID controller which controls the motor, and all of this comes inside a box. Okay, so basically what you need to do is just connect your robot link. Suppose you have one link that you want to connect. So the robot link will just be screwed on here, and it can rotate. Okay, so this is a DC motor in a closed loop control system, and you can control this using a microcontroller, okay, using PWM. So we'll look at microcontrollers. When we talk of microcontrollers, we will be studying how to control this DC servos using microcontrollers and PWM. Okay. So the way the servo motors are programmed is that in the case of a robot, we said that for a link, which is there, the link doesn't rotate 360 degrees. So at most it will rotate like 180 degrees, or it will rotate 270 degrees. Okay, it is not going to rotate completely 360. So these motors need to rotate only 180 degrees or 270 degrees. And how we control it is by using a PWM signal from the microcontroller. What is a PWM? Basically, we give square waveforms and vary the width of the waveform. So this is the width of the waveform. So this would be called the width of the waveform. That's my width. So how much time it is on, this much is on, that much is off. So by varying this W, I can make it move at different positions. So this is already, the PID controller is pre-calibrated. So on one end, it is 0 degrees, and the other end, it can be 180 degrees. On the other end, it can be 180 degrees. Okay. So if the pulse width is 0, it understands that it is 0 here now. And if the pulse width is full pulse, means the full pulse is coming, full pulse will mean this much. Okay, it's the full pulse coming in. Then what it means, it is 180. So by changing this width of the pulse, this link can go and position wherever you want it to go. So the corresponding angle would correspond to the width of this pulse. Okay. So we have experiments with this also, because this is a very simple motor to control with a microcontroller, and a microcontroller can generate a PWM pulse width very easily, and hence it is very, very easy to build very, very simple robots by yourself. Okay, let us look at pneumatic actuators. You have studied about pneumatic actuators, and pneumatic actuators are basically piston cylinder mechanisms. Okay, so this is showing you a piston cylinder mechanism, and you can position depending on the you can go and position this link here. Okay, so for example, if this is a piston cylinder mechanism, you can basically go and position the piston depending on the input pressure and the output pressure. Okay, so hydraulic actuator also has almost the same kind of piston cylinder mechanism. So there is an input on one side and an output on the other side. Okay, so depending on which side is getting activated, the piston will move in that corresponding side. Okay, so this is a piston cylinder. Okay, so there's an input here and an output here. So in here, out here. Okay, so if you charge the cylinder, what will happen? The piston will move this side. Okay, and this will come out. Now if you charge this side, then what will happen? The piston will move this side. So by giving pressurized air or pressurized liquid, you can make it move in any direction. Okay. So these are piston cylinder mechanisms which are mainly used for grippers. Okay, robotic grippers are very often piston cylinder mechanisms, and they are pneumatic. Okay, now the next is smart actuators. Now, electric motors, hydraulic piston cylinder mechanisms, pneumatic piston cylinder mechanisms, they are conventional actuators. Okay, which means that they suffer from the size effect. What is the meaning of size effect? Now, what size effect means, let me explain a size effect here. So what size effect means is, so this is called the size effect. So when we have our closed loop control system, plus minus here, we said there is a controller. Then we have the robot. Then this is a sensor. And it goes back like that. Okay, so the robot also has a motor in there, right? Now what we see is that suppose you want to build a very small robot. Suppose you want to build a very small, let's say NC machine or CNC machine. How small is small? Small, maybe it is maybe 20 mm cube. That's small, 20 millimeter cube. So small lathe, which is 20 millimeter cube. So one way would be that you shrink all of these components of a normal lathe and you make a small lathe. Okay, so you take a big lathe, you make it small, and then you have a small lathe. How small? 20 millimeter cube. Will this work? Now if you think a little bit, it will not work. Why? Because this motor which is there will not be able to, if you make a very small motor, the small motor will not be able to generate that kind of power that is required to cut material. Now when you are cutting material on a big lathe or a small lathe, the cutting forces do not change because material properties do not scale. So if you're cutting 1 millimeter of steel in a big piece of steel or 1 millimeter of steel in a very small piece of steel, the cutting forces will be exactly the same. Why? Because cutting forces do not scale. Okay, so we cannot shrink a robot or an NC machine and make a very small robot. I can give the example of a robot also. So we have a robot here. Okay, so I connect this to a motor encoder and gear. Okay, so what would happen is, if I want to make a very small motor, I want to make a very small robot, so micro robot. So micro robot, what you can do is you can make very small motors. Okay, but in a micro robot, I make a very small micro robot. Okay, but if I make a small DC motor, what will happen is that this DC motor will not have enough power to move the links of the robot, because a small motor, you know that in the DC motor, what happens is the torque is equal to the motor constant into the magnetic flux. Okay, the strength of the magnetic flux in there. So for a very small DC motor with a very small magnet, it will not have enough strength, and hence it will not have enough power to move the system. So this means that if you want to go to the micro or the nano domain, then you cannot use conventional actuators. Okay, so for that we need to go to advanced actuators, which are small. They have low power consumption for micro motion. Okay, so nano motion, micro motion, we cannot go with normal DC motors because a very small motor cannot have enough power to move the system. So in that case, we use this advanced actuators, and advanced actuators like ultrasonic motors. Okay, then artificial muscles, molecular motors. Now ultrasonic motors are like this. They work on the ultrasonic frequency principle rather, and how the construction is a little different from DC motors. So this is the rotor and that's the stator. Now the stator is made up of these teeth. Okay. Now this is made up of piezo material. Now in this piezo material, if I give it a particular charge, okay, so this is my piezo material. If I give it a particular charge, what will happen is this will expand. So the moment it expands, it will tend to push this now. So first of all, there is physical contact in here. So there is physical contact in there. In a DC motor, the rotor and the stator, there is no physical contact. There is an air gap. Here, there is physical contact. So there is physical contact in between the rotor and the stator. Now, the way we move this is we charge it at a particular frequency. So we'll give this a charge, then we'll give this a charge, then we'll give this a charge. That charging is done at an ultrasonic frequency. Okay, so this is done at that frequency. Okay, and this will give a small kick to this fellow, then give a small push like that. So what will happen is this will move in that direction. Okay, so we charge the teeth of the rotors in a particular frequency, and because of which it gives a small push to the rotor, and the rotor moves in a particular direction. If I reverse it, it will move in the other direction. So this is extensively used in small motors, in cameras. Okay, so in the cameras, if you look at the large SLR cameras, where you have the big lens, so let me draw. So this is your camera with the big lens. Okay, so when you're focusing, the lens moves, the big lens moves. That means there is an actuator which is moving it. Now, where is the actuator? If you open the SLR camera from here, if you remove the lens and you look inside the body, okay, what you'll see is that inside here, there is this part is there. And in this part, you can see small teeth. Okay, this small teeth are actually this one. Okay, and they are being actuated one teeth at a time. And on the other side, on the lens, you find is this part, okay, which is the rotor part. Okay, and by actuating the stator in a particular frequency, it moves, and hence the rotor moves in the forward or the backward direction. Okay, now the advantage of this motors is that they are very strong. They are independent of the size effect, so you can make a very small ultrasonic motor and it will still work, because it is working on the piezo crystal. So this is a piezo. So piezoelectric, piezo ceramic, you can make a very small one, it will still work, okay, unlike a DC motor. The next kind of advanced actuators are electroactive polymers, and these are actually polymers. And inside these polymers, you have plus and minus, this cations and anions. So on the polymer, we have this coating. Normally, there's a coating or an electrode of gold or platinum. So this is my electrode, okay, which is gold or platinum. Okay, and if I give it a particular voltage, what happens is that you see that the ions move in a one direction. So if I give it a charge like shown here, all the plus charges have gone to this side. So what happens? The pressure gradient here increases. If the pressure gradient here increases, it bends on this side. Okay, if I remove the voltage, it will become constant again, it will become straight again. If I reverse the polarity as shown here, what has happened is all the plus charges moved on this side now, so it bent on that side. So by changing the voltage, I can make it go on the left side or the right side, I mean clockwise or anti-clockwise. Okay, now this electroactive polymers are water based, so they work underwater also, and you can cut it here and it will still work, because it's independent of size. Okay, so size has nothing to do with it. So if I cut this electroactive polymer, it is still going to work, right? This is an example I had shown, I think, a couple of classes back, where we have this robotic hand, the fingers of which is made up of electroactive polymers. And this is a hand which does not have any linkage. You don't see any joints, any linkages, but it is behaving like a hand. Okay, so this is an ionic polymer metal composite called IPMC, and if you give it voltage, it changes the shape. Okay, so this is an example of a smart material. We talked about smart materials. So this is a smart material. Okay, so if I give it a charge, it is going to, so if I give it a charge, it is going to change its shape. Okay, and it is called a smart actuator because it works both ways. If I give it a charge, it will change its shape. If I change its shape forcefully, it will generate a charge. Okay, But this is interesting because there is no joints, there is no linkages anywhere that you can see, right? Now this, if I want to make a small hand, I just cut the fingers into small pieces and I can make a very small hand. So you have a robot now. Suppose I want to make a very small robot. What I can do, I can make the links out of this electroactive polymer, and now you have a very small robot. There is no joints, there is no actuators anywhere now. Okay, the link itself is an actuator. So these are called electroactive polymers, and the material is ionic. It's IPMC, or ionic polymer metal composite. So this ionic polymer metal composite called IPMC. So this is a polymer which is basically coated with a metal electrode. So either it is gold or it is platinum. Okay, and the material, in terms of the material, is called Naphthalene 117. So that's the material of this polymer. Now there is another. So we looked at smart actuators. We looked at ionic polymer metal composites that I showed just now. We also talked of electroactive ceramics that I talked in terms of the piezo crystal, piezo quartz. Okay, so these are smart actuators. Now in between we can also have shape memory alloys. So shape memory alloy is, or SMA, is basically called nitinol. Okay, so nitinol is the shape memory alloy. Now if you give it a temperature, what happens? It changes its phase. So at a particular temperature, there is a phase change that takes place. Okay, and when the phase change takes place, the size changes. Okay, so it becomes shorter. Now if I heat it again, it will come back to the temperature, it will come back to the shape again. So shape memory alloys can also be used as actuators by changing the temperature of this alloy. Now in terms, when you want to think of which actuator to use, which smart actuator to use, there are three of them: IPMC, SMA, and electroactive polymers. Then in terms of displacement, we see that IPMC has the largest displacement. Okay, and electroactive polymer, and piezos have the smallest displacement. In case of force, IPMCs generate small force, piezos generate high force. Reaction speed, they are more or less same. Now in terms of drive voltage, we see IPMC requires very small voltage to drive, whereas electroactive polymers require very high voltage to drive. Okay, in terms of properties, mechanical properties, this is elastic, this is also elastic, this is a metal, whereas this one is fragile. Now the last kind of actuators are molecular motors. Now molecular motors are the ones that are molecules which are inside our body. So the molecules inside the body, that is the cells, they also move around. Okay, and they move around in the sense that, for example, if you have a cut, okay, the skin automatically repairs. So new cells are generated and these cells move around, and they are called molecular motors, which work at the molecular scale. Okay, so today we talked about sensors and then we completed our discussion on actuators. So in the next class, we'll move on to linear basics of linear control systems. Okay, and where we'll talk about how do you actually control. Now that you have an idea of sensors and actuators, we connect sensors and actuators in a closed loop control system, and then we can basically try and control a link to take it to a particular position. Okay, or we can have a mobile robot which can move around and avoid an obstacle. So these are all applications in robotics that we'll be looking at as we are slowly going forward. So we'll stop here today. Thank you.